All right. Hi, everyone. My name is Moses Sampal, part of Quantum Computing India team. And so this is Cryptography August. So this entire month, we have been doing sessions around cryptography. And the first week, we had a session around cryptography basics. So we understood the need for cryptography, typical, symmetrical, asymmetrical, what are the major algorithms that we currently use, what are the applications. This all happened in the first week. And in the second Saturday, we had a session by KG. So he took us through implementing these classical cryptographic algorithms in classical computing, right? Like with Python. So even the notebooks of that are put up in our Discord channel. So if you have been, part of our team, you would have known that. Now the third week, which is today. So we have Dr. Urbasi Sinha with us. So she'll be taking us through quantum secure communications. But let me quickly also talk about the next week and what happens after that. So the next week, we have Dr. Anindita from QNU Labs with us. So she'll be talking with respect to what QNU Labs is doing and how the QKD is being adopted by the industry in terms of retrofitting. And so then after that, the week after that, we'll be essentially picking one or two use cases. And as a team, we'll be working on that continuously as a hack series. So that's the plan. Now, with that as the context for Cryptography August, I take this opportunity to welcome Dr. Urbasi. I'll quickly read a bio about her. So she's a professor at the Light and Matter Physics Group at Raman Research Institute, RRI. She joined in 2012 and now heads the Quantum Information and Computing Laboratory as well. The lab specializes in experiments on photonic quantum information processing, including quantum computing and quantum communication, primarily using single and entangled photons. She's heading India's first project on satellite-based secure quantum communications, quantum experiments using satellite technology. She's also an associate faculty member at the Institute of Quantum Computing, University of Waterloo, Canada, and the Center for Quantum Information and Quantum Control, University of Toronto, Canada. Before joining RRI, Urbasi was a post-doctoral fellow at IQC, Institute for Quantum Computing, the Canada Waterloo University. She was involved in quantum optics-based experiments involving production, manipulation, and application of heralded single photons, as well as device fabrication for solid quantum devices based on nanowires and carbon nanotubes. One of her noted pieces of work was a novel experimental test of the Bond rule for probabilities in quantum mechanics. Prior to her postdoctoral stint at IQC, Urbasi was a postdoctoral research associate in the Cavendish Labs Department of Physics, Cambridge, UK. She completed a PhD in Cambridge on experiments in high superconductivity, high TC superconductivity. Yeah.
Transition, yeah.
Okay.
High transition temperature.
She completed her MSc in physics, also from Cambridge. She has been a Gates Cambridge Scholar during a PhD and a Nehru Chevening Scholar during her master's. In recognition of her scientific achievements as well as outreach activities, she was awarded the Homi Bhabha Fellowship in the year 2017 and has been named as the recipient of the 2018 ICTP ICO Galeno Denado Award in Optics. She was recently recognized as one of Asia's top 100 scientists by the Asian Scientist for the year 2019 and has been awarded the Simons Emmy No Ether Fellowship at the Perimeter Institute, Canada. And thanks a lot for doing this. Just reading this, puts a kind of to-do list for me to go back and read on the topics at least. Thanks a lot again for doing this, ma'am. And one thing that's not mentioned here is she's also working on the policy draft for India-level quantum computing policy. With that, I'm going to let Urbasi ma'am take over and give us her thoughts on what we are doing and today's topic as well. Thanks a lot, ma'am.
So thanks a lot. So I'll just stick to Moses for now. It's a long name. Yeah, so thanks a lot, Moses, for this very kind introduction. You reminded me, and yeah, it's very humbling to actually have that read out. But then, yeah, thanks a lot. And of course, thanks to the Quantum Computing India team for being in touch and for pursuing this and making this happen. So what I'll do is I'll of course share screen too, because I'll go through a presentation on secure quantum communications, and the idea is that we will discuss a little bit about what it is and what are the various ways of doing it in terms of secure communication, and then what we are working on at RRI, and then what we see will happen in future. And of course, yeah, so I don't know how this works, so you can ask questions during or after, or
Ma'am, it's really up to you. Usually we take in questions on chat, and
then you do it in the end. Yeah, that perhaps maintains the flow, but then yeah, so I'll go with that. So thanks a lot. So I'll share screen and then remove my own view. Okay.
Yeah.
Just 1 second. Let me just go to slideshow mode. 1 second. Okay, can you now see the first slide?
Yeah.
Okay, great. Yeah. So what I wanted to do is essentially discuss the topic of secure quantum communications. And of course, I'm at RRI Bangalore and with these affiliations. Okay. So what we do is basically work on various applications of single and entangled photons. And we work on things beyond quantum communication. So we work on quantum computing, quantum information processing, quantum optics, everything that one can do using photons in quantum technologies. So we cover that through different projects. And so if you wanted to have, and because I know that here we have people who are actually interested in knowing more and learning about the subject and so on. So this is a review article that we were invited to write on single photon sources, which may be of interest to you because it gives you a perspective of the different ways in which people can, you can actually manufacture these photons. So the idea being that, you know that a photon is a particle of light, but then it's just easier said than done in terms of actually making them. So you just can't take a light source and just dim it down and have a single photon like that. So there are different technologies through which you can do that. And this article kind of covers that. And also if you wanted to have do you also see this thing called UR screen sharing? Do you see that message also on your screen?
No.
Okay, then that's good. Yeah, because then it's for me only. Yeah. So then you can essentially also have a look at this article that was written on our lab's work, which is also from a little bit of a general perspective on how we are working on quantum computing domain using photons. And this is the Raman Research Institute, by the way, and it's of course also in Bangalore. But at the moment, I wouldn't advise you to come and visit for various reasons. But hopefully soon we'll reach that situation again where we can have visitors back and forth. And this is an overview, a snapshot of various experiments in the lab. And this is essentially how experiments look in a quantum optics lab. And these are different things in progress, different research directions. And if you wanted to have an overview of our lab and its various activities, so we spent quite some time in developing our lab webpage. So you can find details about our quantum communication, computing, quantum optics, and fundamental quantum mechanics and QIP experiments and theory. So just please feel free to go and have a look, which has all sorts of details which we won't cover today. And of course, these are all various people who have come and gone from the lab. And they are in different locations after having done various internships as well as other degrees from our lab. Okay, so as I mentioned, our current areas of focus are on photon sources and how to make them, and then of course use them in quantum technologies. And these are some pictures from the lab. So this is actually a picture that you would find a different one. This is from our lab, but a similar one you will find very much on the internet if you look for entanglement. So this is a picture which summarizes quantum entanglement actually. So these photons, when they are emitted from the source, they kind of come out. I do hear my own echo. Is that something from your end, Moses?
Ma'am, it should be
I
fine.
can hear myself sometimes. Okay, yeah. So then these photons, they actually come out in the form of cones. And that is because of some equations that we won't get into that. But they come out in the form of cones. And so then when one of the photons is on one of the cones, then the partner photon is on a different cone. And so they always come out in pairs. And so that's why they are called pair photon sources. Okay. And the idea is that in an entangled photon source of this kind, if the photon is on this cone, this partner is on this one. But now if you see my mouse here, I'm at this yellow region here. Here you do not know which cone the photon has actually come from, right? Because of course, it could come from this or that, because it's an intersection point. And so this is what forms the entangled state, actually. So this particular intersection is where you have the entangled photons. Because if one of them came from the right cone, then we know that the other one definitely came from the left one. But before we know this, we cannot know that. And so that is why they are, you can't define the state as individuals. You have to only define it as a total, as a whole. And so that is why we say, an entanglement is more than the sum of parts. And so this is how you can create entanglement in the lab using photons. And so this is essentially the idea. This is a cartoon schematic of how, you go through various optics. This is a nonlinear crystal, and then you have lots of optics. And then ultimately these photons, they come out in the form of cones. And as I was saying, that these would form the entangled pair, because if one is here, the other is here, and if one is H, then the other is V, but otherwise we don't know. So it forms what is called the HV plus minus VH state. And that is the idea of entanglement. And this is how it looks in the lab. Lots of optics, and ultimately these photons are connected through optical fibers to dedicated photon detectors and so on and so forth. And then we find out the state of the photon through what is called quantum state tomography. Before I go on to the topic of quantum communication, I would like to give you a little brief overview of other activities in the lab, because that gives you a perspective, and then we'll go on to discussing communications. So one of the things which we do, and in fact we have a lot of, we do it very seriously, is actually fundamental tests of various principles of quantum mechanics. So whatever we hear today and whatever we've heard before or after, people will tell you that they are able to do what they do because of various principles of quantum mechanics. So you heard about our experiment on the Born rule. That is one of the postulates of quantum mechanics. So similarly, there are others like the superposition principle. Maybe you're hearing about that in your quantum computing talks that you must have heard. And then there is entanglement. So these are all properties of the quantum system. But then the point is that, these are there and we are using them in these technologies. But then what is also true is that a large part of the universe is something which we don't really know, like maybe even 90%. And that is what we call dark matter, right? So in some sense, there's a lot of the universe which is unknown to us. And then it is not correct for us to just assume what we know to be a foolproof. And so one of the things which we and other labs invested in quantum technologies does very seriously is actually do precision tests of these principles of quantum mechanics. Because if you put a bound on these principles, then you will be able to know how far you can go with the technology which is based on these principles. And so this is what we mean by fundamental tests of quantum mechanics. And here you see an experiment which we have done, in which we have tested the superposition principle itself. And so this is a series of work in theory and experiment, where this one is the first experiment which tested this ever. This correction term to the superposition principle, which we ourselves had proposed in a previous series of work. And so similarly here you have the fundamental quantum optics experiments. And again, if you're going to actually use photons towards something, or even anything else, it need not be just photons, but then you rely on certain properties to hold. And so one of them is this bunching effect. You've heard of this bunching and anti-bunching effects. And so two photons, when they are incident on a beam splitter, they always bunch and they go out one way or the other. And that is what leads to a dip when you measure their correlation function. And so this is called the Hong-O-Mandel dip, after the three people who invented, who kind of found this effect. And so what we have done is a first experiment to show that this can also be done in classical domain. You don't need quantum. So one of our areas is to figure out how far we can stretch what we know in classical and where exactly quantum kicks in. So this is what is called the classical quantum boundary. And one of the papers which recently got accepted in Physical Review Letters, which is a very prestigious journal in physics, day before yesterday even, is again something in which we've come up with a new technique to actually measure the state of the system. So all that is fine. So you're using the state, you're manipulating it and so on. But then what is the state is something that is a question. And what is the best way of figuring this out? Because if you measure something, you know that you have lost it, right? So that is the collapse. You must have heard this in some other lectures. So then what is the way in which you can do this by minimum number of measurements without, essentially with very high fidelity? And that is what we have established in this work, this very recent work. Then going on to quantum computing, as well as quantum key distribution actually. So you hear about devices being used, solid state devices, which are used for quantum computing. And these are based on semiconductors or superconductors and so on. And so one of the things that happens there is that people restrict themselves to using what are called qubits, which is essentially a two-dimensional system, right? And this you have heard. So qubits and manipulating qubits through quantum gates and so on and so forth. So one of the things which is very much in the news and for a group like this, which is interested in this domain, you would know about this quantum supremacy, which was claimed to have been achieved and so on. So what is this thing? So this thing was the idea that if you attain a quantum processor with 50 or more qubits, then you have kind of crossed a certain threshold, okay? And so you're able to do certain problems in real time with that exponential speed up, which otherwise you are not able to do in the classical domain. And so this 50 was and is an important number. And so now the 50 becomes important because the number 2 to the power 50, which is what gives you that exponential dimension in Hilbert space, is very large. It's actually proportional to the age of the universe even. So now that is why 50 is important. But now think about it. If instead of the 2, I replace the 2 itself with something like 3 or 4 or 5, then the number 50 would drop, right? So 2 to the 50 will be similar to 3 to the 33 maybe. And then if you make the 3 4, then the 33 will drop. So if I increase the base, then I actually have access to a similar state space dimension as with the 2 to the 50. And that is what is called higher dimensional quantum computing. And this is a very interesting area because there are lots of open problems in this. People have concentrated a lot on qubits and we have reached a certain level. But this is an alternative approach where we are trying to find out how far we can go by increasing the higher dimension. And so here you see a picture of our experiment where we have actually attained higher dimensional quantum bits. It's a two-qubit system, which is also highly entangled. And so this sort of sets the basis for all these explorations we want to do in higher dimensional quantum computing and key distribution. And if you wanted to know more details from a general perspective, again, there is an article that I was invited to write for Scientific American, which is a very interesting science magazine, maybe you're aware of, where you can find, some description on this area of higher dimensions that we are pursuing in our lab. And then, of course, so one of the things which we are very interested in doing is, finding out and learning more about quantum measurements, because that is one of the most interesting areas, which is where there is a lot of open problems as well. And we are working on different areas called generalized measurements or weak measurements, where you can actually do certain things which you cannot even think of doing using the conventional measurements. So just to give you an example, in a conventional measurement, when you're measuring something, then you know that once you measure, you collapse the wave function, we say, right? And so that is what is called a strong projective measurement. But if you do what is called a weak measurement, then in an ensemble sense, you can actually gain information about the system without disturbing the system, which is a kind of counterintuitive to our usual notion of what we learn. But then weak measurements is also very usual. It's very highly mathematical in its concept, in its structure. And we have used that successfully to do many things which otherwise would be quite difficult using strong conventional measurements. Again, thinking of it as a technology tool. Studies of entanglement is something which fascinates us because, of course, we use that in our quantum communication as well. And so we are constantly on the lookout for brighter and higher fidelity entangled sources, manipulating the entanglement, trying to prevent the entanglement from degrading. The experiment you see on screen is to prevent it from degrading. There's something called sudden death of entanglement. And it is exactly what it suggests, that suddenly the entanglement drops to zero. Because of interaction with the environment. So we have come up with a scheme where we can prevent this from happening and so on. So this is, understanding this phenomena better so that we can use it better in our quantum communications and other domains. So on that, I would like to now move on to quantum communication, which is the topic of today's discussion. And of course, the first question is why you should worry about it. And it's of course, I'm hoping that some of you already know the answer to why you should be worrying about this field. And why you should be worrying about it, because this actually is something which is going to prevent our current communication techniques from being jeopardized with certain advances. So for instance, the four things that you see highlighted here, I'm sure at least the first three we are all involved in. Whether we are nowadays with the COVID situation where I'm giving you this talk from home, it's an example where we are doing things online even more than ever, right? And so many things are going online, and so then we have to worry about how secure this transaction is. And of course, the defense is very important, and we perhaps maybe don't worry about it ourselves, but then there are people who worry about it, and we need to help them. And so all this is at being risk, of being compromised with quantum computers. And so we will, so essentially we will know how in the next few slides. And so classical cryptography is what we need to kind of counter with a quantum counterpart, and which is what is called quantum cryptography. And so these are all examples of various communication devices which we are all using, but not necessarily so secure. I mean, if the television broadcast is not meant to be secure and so on. So that is okay. But then if you want security in the communication, then what you do is essentially you have a sender and a receiver, and we actually are encrypting this message using a key, which is then being distributed and then this key is again also available to our receiver here, who's using it to decrypt the message. So only the sender and the receiver essentially know what was intended to be sent. But then we can have an eavesdropper in the middle who might try to find out more about it and then jeopardize this communication. And so that is what we will see a little bit in detail as to how that can be somewhat prevented by using a quantum means of distributing this key. So this is what is cryptography. This I suppose you've been discussing over the last couple of weeks. So essentially you have this message, and then we have this is a simple example. So this is the this is the number counterpart. This is so we basically have the ASCII, and then we have a key, and then we've done a simple operation, and then we have then undone the operation. So it's just an example to show how it works. You have private key, and then you have the public key. And so the public key is, of course, what has the problems that we will be discussing. So the Diffie-Hellman and the RSA, these are common methods of key distribution in the public key domain. And the essential idea here is that these and others like them are based on a mathematical problem that is easy to compute but hard to crack. And that is the basis for such protocols. So now this slide is an example. It's a toy example to tell you about the difference between a hard and an easy problem. And so the thing on the left that you see is a situation which is very easy for most of us to create. But the situation on the right, only some of us take the burdens of doing this, and it is not as easy as the left one. And so that is why, how do we distinguish between the easy and the hard here? That is the time it takes to actually do this problem, right? So just making a mess with clothes, it takes very little time, but sorting them out color-wise and putting them in the cupboard and so on and so forth takes a lot more time. And so this left is an example of the multiplication problem, let's say, whereas the right is the factorization problem. So that is the idea. So amount of time it takes for you to crack a certain problem kind of tells you about what hardness class it belongs to, essentially. And so that is the problem that we will face with classical cryptography, because this hardness class could perhaps be changed with the advent of quantum. Okay, so in classical cryptography, unconditional security is not possible. For instance, as we just discussed, the RSA protocol. Now, this is based on the mathematical complexity of factoring large numbers. And so these are some numbers about how much has been done in factoring large numbers. But then typical RSA is 1024 or 4096 bits long, let's say. And Shor's algorithm, and this is Peter Shor, by the way, is an algorithm which uses quantum gates, which can perform factorization in polynomial time. So essentially something that we thought was secure because the factorization was such a hard problem need not really remain so anymore if Shor's algorithm starts kicking in and working on quantum computers. So essentially this slide summarizes the need for quantum key distribution. Okay, so computational resources, they grow very fast, and today's hard problem could be solved tomorrow using brute force attack. So we need new algorithms for classical, I mean, not new, I mean, not need, sorry. We can have new algorithms for classical computers, or we can have realization of quantum computers, which is of course definitely going to happen. So my security should be independent of future advancements in computational power, new algorithms, or new technology. That is, it should be future secure, a very important phrase here, future secure. So what I think is secure today should remain so even 10 years down the line. And so this brings forth the need for quantum cryptography, where security is based on laws of nature or laws of physics and not on the mathematical complexity of a problem, which indeed can be broken either by new algorithms on existing devices or new devices which are getting built at a very fast rate. And the most important part of this process is the key distribution itself, which is why we call it quantum key distribution. So one has to understand that in quantum cryptography, we call it quantum cryptography, but it's not quite right to call it quantum cryptography. It's basically cryptography using quantum key distribution is what we really mean mostly. So because the encryption and the decryption, those parts are still done using standard algorithms. It's the key distribution which we have now secured using quantum means, which basically does it for us in terms of getting the communication to be secure. And so quantum key distribution is kind of the quantum part of the story. And so this is a slide which tells you about where we are with the RSA cryptographic protocol. And Krista's comment here from Microsoft Research is very interesting. So he says that the RSA 2048 challenge problem would take 1 billion years with a classical computer. A quantum computer can do it in 100 seconds. So this is of course what Microsoft believes. But please bear in mind that this last line which I have added here, that a quantum computer will employ Shor's algorithm, of course, to solve the factorization problem. It is estimated that this 2048-bit RSA key could be broken on a quantum computer comprising 4,000 qubits and 100 million gates. So this is important that, you know, it's not like today we really have this technology with 4,000 qubits and 100 million gates. But then that need not dishearten us. If you hear that now, if you think, oh, the number 50 seems small to me because I really need 4,000, so I need not worry. That's not true. Because you see, even the rate at which this progress is happening in terms of increasing the number of qubits is not linear. So there also we have some kind of a quantum Moore law, which is not a Moore law, but a quantum version. And also one has to take it with a grain of salt. This qubits, you know, whether the qubits are physical qubits, whether they're logical qubits. And so this sort of things are details, and I'm sure you're hearing about them in other discussions. But this number is not unattainable. And in some sense, we need to worry. So if you want to worry about something only when the problem is already there, then that's already too late. So you need to worry about it a few years before this problem actually happens, because we are already working towards having the problem happen, right? So quantum computing is, of course, a very active research area. We are working on it. But then the downside is that it can actually break these codes, which we don't want it to break. And so we need to start preparing ourselves for the challenge from now. And one method would be quantum key distribution. It need not be the ultimate thing. But then having said that, that is the most advanced technology that is currently available to us to circumvent such problems. And of course, there are already lots of companies and stakeholders who have made lots of claims in the domain of quantum computing. And so this is the general setting of QKD. So Alice and Bob are connected by a quantum channel into which Eve can tap without any restriction other than the laws of physics, and by an authenticated classical channel into which Eve can only listen to. So this is what we kind of base things on. And laws of physics are kind of difficult to break, so so it's not easy for Eve to actually do this tapping. So how does quantum mechanics protect information? So we will discuss the actual principles. I mean, not in great detail here, but the idea can be summarized as follows. Measurement disturbs the signal on an average. So if the signals are non-orthogonal, the idea being, like say the horizontal and the vertical are two polarization states which are orthogonal. But then if these signals are not orthogonal, so let's say, so for the off and the on switch are orthogonal. But suppose we have an off switch and then we have a partially on and a partially off switch. Or if you think about it from the spin perspective, you have a spin up and down, but if you have something in the middle is not orthogonal to the up and down. So, and in a common sense terminology, if you think about the globe, the north and the south pole, of course, are what we call orthogonal, but something like the north pole and something in between the equator and the north pole are not orthogonal. So if you have signals in that domain, then the adversary cannot ascertain which one it is actually. And there is maths to prove that. And unknown quantum states cannot be cloned by an adversary. This is, of course, one of the important principles called the no cloning theorem. So if an adversary is trying to simply copy something and then use it later, then we would know because of the no cloning theorem. So this is another principle which kicks in. And then, of course, quantum correlations like entanglement, they can be used to protect information. So these are basically the ideas which are used to protect information using quantum mechanics. So this is, so now it brings us to, different ways in which entanglement, in which quantum key distribution can be done. You can use it without using entanglement. And this is an example of that. The BB84 protocol is an example of a protocol where we don't use entanglement, but we use the uncertainty principle or the no cloning theorem for non-orthogonal states to protect the information. And then here you have an example in which we are using entanglement to protect the information. And our lab is actually working on both these topics, and we have established both these protocols in our lab. Okay, so now just to go over quickly the general idea of the BB84 protocol. The BB84 is perhaps the most well-known quantum key distribution protocol because it's the first one. It was established in 1984. And very interestingly, the anecdote here is that it was actually a conference proceeding of a conference which happened in Bangalore. So there is a BB84 actually has a Bangalore connection as well. And so here you have, this is what we mean by this non-orthogonal state. So you have the 0 and the 90, these are orthogonal, whereas the 45 is non-orthogonal to the 0. 45 and 135 are orthogonal to each other. So you can have two bases, two orthogonal bases. One is the 090 and one is the 45 135. But to them, each are not orthogonal to, they are not orthogonal to each other. So 45 is not orthogonal to 90. For instance. So that is the idea. So let us see how this works. So here I have a single photon source and I have Alice, and here I have Bob, and certain things will happen in the middle and we will have the measurement. So I'm going to use some color encoding to make this animation a little more interactive. So I would say that, if I have the rectilinear basis, rectilinear is basically the 091. So if I have the rectilinear basis for 0, I will use a red symbol, and then for the diagonal, which is the 45 135, that 0 I will use the yellow, and similarly the rectilinear 1 I will use blue, diagonal 1 I will use green. Okay, and so I have a single photon source, it has emitted a certain photon. What I need to do is encode it with this information, this basis information. So the encoding step is what I need to do next. And so Alice actually then does this encoding using randomly, of course. She randomly selects one of these 4 possibilities and encodes that on the photon. And so what I have here is the red encoding, let's say. And this is what Alice stores down below. And so then it goes to Bob. Bob, of course, also has a random selection of bases by which he decodes it, and then he measures. Okay, and he measures and he finds that, he has actually measured it because it's random, you see. So Alice is creating it randomly, Bob is measuring it randomly. So when Bob randomly measures, he could choose the diagonal basis, and then the answer he will get is 1, which is not quite what Alice had sent, by the way, right? So this is the idea. So Alice actually will encode in one of 4 possible basis choices. Bob will decode in the same one of 4, but not the same one necessarily, because he doesn't know what Alice has done. So randomly he will pick one. Sometimes it will match with Alice, sometimes it won't. And so when it doesn't is the first example we have seen. Similarly, this one goes through, and here again he chooses the different basis. Okay. Now again Alice has sent. Here Bob has chosen the same basis as Alice, and so both of them now have the 1 bit. So Alice had also encoded 1, Bob also received 1. Okay. And similarly we have other examples. And so then this is the idea that you can keep on doing this. And then what happens is, over a classical channel, Alice and Bob will actually share their basis information, okay? Not anything else. Alice won't say what she has measured in terms of the bits. Bob also won't say anything. All that they will share is their basis information. So Alice says rectilinear, diagonal, rectilinear, rectilinear, DD, and Bob says DRR, DDR. Okay, that's all they share, that are the basis information. And so by sharing it, they now know where they had matched and where they hadn't matched. And so these are the ones they cross out where they did not match, and only they retain the ones in which there was matching. And so this is what we call basis choice sharing. And then finally you have what is called the raw key. Okay, so Alice's operations: prepare single photon, different types of sources including weak coherent pulse. SPDC is the source we use, which is more single than the weak coherent. We can discuss that later if we wish. Random selection of polarization basis for each photon between rectilinear and diagonal. Random selection of polarization between two orthogonal states in each basis, because even in rectilinear you can have 0 and 1, and in diagonal 0 and 1. So that, and then you record the time stamping and polarization state for each photon. Okay, and she then sends the stream of photons to Bob. What Bob does is the reverse operation. So he does random selection of polarization basis for each photon between, again, the same basis, measures each photon in the selected basis, records time stamping and polarization state for detected photons. So together, Alice and Bob's operation: send time stamping and basis selection for each photon over classical channel, compare selected basis for correlated events, consider only those events where basis choice match, and discard the rest. Right? Okay, so that is how we have created the raw key. So what have we done so far? Alice and Bob have shared a common set of binary data. First, we had the raw key. After basis information exchange, we have what is called the sifted key. So please bear in mind, sifting is this thing, you have this wheat and you have this sieve, whereby, you're kind of getting rid of what you don't want. So that is the idea of sifting, okay? And so once you sift out what you don't want, you are left with a sifted key, okay? So now the point is, how do we make the key secure? So there, there is a concept of what is called a sacrificial key. This is a statistical set on a subset of the data. So you already have this sifted key. So for subset of the data where the bit values are also announced, not just the basis. So you compare actual bit values. If they are the same, then one can conclude that the rest of the key follows the same logic and Alice and Bob share the same data. If they are not the same, then you have certain thresholds up to which you can, live with the non-sameness, and beyond that you don't. And so this is a small amount of the key which is used to test for the rest of the key. Okay. So assumption. So now, of course, in practical quantum key distribution, there are certain assumptions which we have made so far which will not hold. So in assumptions that we have made so far, that Eve can listen to signals, but Eve cannot change signals. And this is not practical, because of course what we do is we consider what is called an omnipotent Eve. Omnipotent is someone who knows all. And so Eve actually is supposed to know all and have all the powers. So if that is the case, then of course she can do other things than just listen. So in real world, Eve will not only listen, but also manipulate. And there are also always errors in implementations of QKD. Okay. And so this is my handwritten thing I put together quickly. And so the idea is that, if you have a normal scenario, then you have a message and there's a key established between Alice and Bob, and they both have this message. But then in a different scenario, in a practical scenario, there could be an Eve who's listening in between. So the message then goes from Alice to Eve, and then it can go from Eve to Bob, right? So Alice and Eve will share a key, and Bob and Eve can share a key. And so if Alice uses the key, Eve can decode the message. So this is what we call the attack scenario. And this is what we want to, of course, prevent. And this will happen in practical QKD. So we need to make it hard for Eve, right? And so we need to ensure that Alice and Bob actually talk to each other and not through Eve. And so there is a solution based on cryptography to make sure this happens. And this is called message authentication. And here we need the concept of a seed randomness. So essentially a secret key is shared between Alice and Bob to authenticate the channel. And so, this is something just I've put in for completeness. We are not discussing details here because these are all mathematical steps. These are algorithms which one can execute, hashing and tagging functions. So you take a long key, convert it to a shorter one, then you compare the tags, and then you know whether Alice and Bob are really talking to each other. And so the timing is very important here because it's because of the timing. So if you do it at some other time, then Eve will not be able to gain any information. So it has to happen exactly at that time that Eve has to also come in here. And so then we will know her presence by comparing these tags. And so do quantum key exchange, immediately after that do authentication. And if Eve manages to break the authentication later, it does not matter, because the secure key exchange is already done. So this is just putting it in a very short manner. There are lots of steps involved here. Also, implications of error. So Alice and Bob don't share the same secret key. This will have adverse effect on the message being transmitted. So error is a signature of an adversary trying to intercept signals. But the worst case scenario is all errors are due to adversary, but that's not true. Errors can happen because of the use of certain instruments as well, and the use of certain physical processes. And in fact, what we have done from our lab as a very important establishment is that we have come up with a way in which how you can actually simulate these errors. And we will come to that shortly. So quantum mechanics gives us a way to bound Eve's knowledge. How much Eve knows is a function of how much error Eve introduces. So this is what leads to what is called privacy amplification. We won't go into the details of that. So essentially the critical elements to be developed in QKD, you have the quantum source, you have QKD simulations, then you have the QKD protocol, you establish a key, then you have the sifting to have the sifted key, then you do privacy amplification, error correction, finally you have a secure key. So these are the basic steps in development. Similarly, there is a protocol called the B92, which is also a prepare and measure protocol. So as we said that, there are two types. One is the prepare and measure, and one is the entanglement base. So B92 is essentially a modified version of BB84. The only difference here is that instead of using 4 bases, we use 2 bases. Okay, and so this is again a single photon source. The same thing. You can see that this is similar to BB84 with the difference that you don't use 4 bases. So you have the source. It can get in, again, following the same analogy, and so you can have either the correct thing or the wrong thing. Of course, these are the only 2 possibilities. So you can have 1, and on that side you don't get 1, and here you have 1 and you get 1, and so on and so forth. And there again, the classical channel, you can share the timing information, and then you can again end up with a key where both Alice and Bob have the same key bits. Here you have been able to do this using 2 bases only. Okay, and so essentially again the same thing. You prepare the photon, you have a random selection between V and plus. As I said, it's not age V plus minus, it's only V and plus. So you select between V and plus. Please bear in mind, V and plus are actually non-orthogonal, and that is what gives us and this was Bennett in 1992. He came up with the B92 protocol. And so you then record time stamping and polarization state and send stream of photons to Bob. Then you have Bob, the reverse operation. But here, one crucial difference, that if Alice is encoding in V and plus, Bob will encode in the orthogonal H and minus. And that is how all 4 basis states are actually playing a role here. But then you don't have to actually encode and decode in all 4. So it is better from the practical purpose because you need less instruments and less investment in some sense. So this is, this is a similar thing. And then compare Bob's time stamping data and consider only correlated events, discard the rest. Okay. Then we come to the need for entanglement. Why do we need entanglement in quantum key distribution? So this is just a cartoon for entanglement. Essentially, the idea being that there is a person C who's emitting these 2 correlated photons. They are going to A and B, and till they reach A and B, we don't know whether it's the red or the green which they are receiving. So A asks, what are your, what colors? And B says, no idea. And then he declares that I have green. Then B says, mine must be red. So that is the idea. So once you know what is happening at Alice's end, then then Bob's end also you will get to know. And so how does Birbal know? I mean, this is my student, wanted to have an Indian touch to it. So instead of Charlie, Alice and Bob, we have Chanakya, Akbar and Birbal. But the people who remember their history will remember that they are not from the same time period. So it is a very funny cartoon that my student came up with, but I let it be because, it involves some sense of time travel also, which is always very nice. So, but then, that is the general idea. And this is your AB plus AB by root 2. I mean, that is entangled. And as I say, I mean, entanglement is something I'm extremely, fascinated by. I mean, of course, many things I'm fascinated by, entanglement being one of them, that, it kind of is something which makes things possible which otherwise wouldn't be. And so this is my pet example of how to discuss it with the general audience. And that is this, that, when you hear these various pieces of music in an orchestra, you hear the pianist or the cellist separately. Of course, it's beautiful, but then you don't really get the whole feel for the piece that they are playing, right? So only when all of them play together that you get the symphony that you intended to actually hear. And so it's together that they are conveying something which is much more than what would happen if we just let them play it separately one by one. So entanglement is like that. So it is something more than the sum of parts. And so only together it makes sense. If you cannot just write it as a separable state. And so it's like a quantum orchestra is how I like to look at it. And why is it important in quantum key distribution? And this is, of course, a very interesting reason, part philosophical, part science. And so that is because, how much do we trust our devices? So, of course, when I talk about prepare and measure protocol, I'm saying we have a photon source. That's how I was beginning each slide. Of course, we are making it ourselves in the lab. But whatever it is, we are actually using certain components which we are buying, right? I mean, you can't be making all the elements yourself. That doesn't happen. So you will buy it from someone. And so you have an implicit trust on this manufacturer. The question is, how much do we trust our devices? So what about security vulnerability, which may be introduced at the device level itself? And so that is why, if you want to go a step further, then we need QKD, which is device independent QKD. And entanglement with QKD is the only known route towards device independent QKD. And longer distances are also possible through entanglement-based swapping repeaters. Why I say it's part philosophical, because here we are actually raising a question about trust, right? So we are saying we don't trust the device manufacturer. And of course, we have to be practical, because all this is for security. So we cannot go emotional and say, no, we trust the device manufacturer. So we can't do that. And so that is where this comes in. And this is the ultimate in QKD, a fully device independent QKD, which is not quite there yet. So we are at measurement device independent QKD domain. And that is why our lab, we are working on entanglement based QKD a lot as well, because we want to actually take this to that step. And so this is the idea. So you have an entangled photon. So I'll skip the protocol here. And this is an example of an entanglement-based QKD protocol, which is called the BBM92, Bennett-Brassard-Mermin. So this is an entangled version of the BB84, and where entanglement is used as a resource. I'll skip the details of this one because it's a little involved. But then having said that, this is something that we have established as well in our lab. And we can't say too much more about that development because of a non-disclosure agreement that we have with ISRO. So I can tell you a lot about what has already been published, but then not a lot about what has not yet. So this is one such example. Okay, so this is, it's very interesting because I'm talking to myself, I'm looking at the screen, and I've also ensured that I don't see anyone else. So that I can see the full screen. So I'm hoping that people are still there. Moses?
Yeah.
It'll be good. Great. Okay, yeah. So then on that note, because it is very weird to give these webinars. At some level, when I'm in the auditorium, I actually see people looking at me. I tell them not to look at their phones and all. But now, of course, you can do that as much as you wish. Only I can't, right? So on that note, I want to go on to what forms the basic aim of all this so far as our lab is concerned. Of course, we have done quantum key distribution, we have established prepare and measure, entanglement based, all that is done. But what we really want to do is increase the distance over which such communication can happen. And that is what leads to long distance quantum communications. And our project is called Quantum Experiments Using Satellite Technology, or QUEST. And so the idea is that we have a ground station here, and we have a ground station somewhere else. And we use a satellite as a trusted node to establish a quantum link between these two ground stations. And why we would do that, we just come to that. So why satellites for QKD? Because there are distance limits for quantum channels. So now all that I have been saying so far, I've of course been talking about lab-based demonstrations, and you can take it a bit further and so on. But even if you go ground-based, which is, of course, the usual, you are on the ground, and very much we are grounded people. So we are on the ground, and so Alice and Bob are communicating and they are exchanging a key. The typical distance that you can reach with ground-based QKD is around 100 kilometers, okay? And demonstrations can happen, let's say, up to a maximum 300 kilometers. So what happens beyond that is you don't see each other. So essentially, I mean, of course, we know the earth is round, and so essentially the horizon becomes a problem. So you, beyond a point, it is not very viable to continue doing this by line of sight. And so that is why there is a natural limit to ground-based free space QKD. Then you can use fibers, for instance, as an example of fiber loops and so on. So, but then fibers also, they have losses, right? So this is the kind of typical loss. So beyond a point, you can't do fiber-based either, because of course, if you, what do you do in usual communication is, of course, through fibers, we have these repeater stations, right? So each, after some distance, we have a node where, you know, there is some kind of a device which is, you know, amplifying the signal, and then it is going to the next station. So there is a classical repeater involved in these fiber-based, excuse me, classical, I mean, you know, communication. So, but if you do it in quantum, then, I mean, we have heard about the no cloning theorem. So you just can't do it in the same sense as the classical. So these are the problems with free space and fiber-based QKD. So if you want to go to longer distances, you need to do something different. And so one of them is trusted repeaters. And in fact, this is a bit outdated. It's not underway. In fact, there is a 2,000-kilometer network now, which is the Beijing-Shanghai link in China. So they have been able to actually link Beijing and Shanghai using some trusted nodes and QKD. So this is one way of doing this. Or you can use entanglement-based repeaters. We will just discuss a little bit of that in the next slide. And then, so these are all at the research level. Like the Beijing-Shanghai link is not at the research level, it's already existing, but then it has its own issues. It's not quite, there is this thing of trust. So you have to trust these nodes. So the two ways in which the global community is trying to increase the distance is by, you know, understanding the repeater technology better, or by using satellites. So our satellites, so I don't know what is my, so the satellite we will come to, we have another slide on that. Let's just study a little bit about these relays, memories, and repeaters. So this is the idea. So, I mean, you know, this is the idea of a relay. So you have two teams, and, you know, we used to play this when we were younger. At least I'm sure there are people who are still playing it in this audience. Maybe you are very young. But then having said that, you had these two teams, and then one person would have this thing that he would run and give it to the other person in the other team, and then she would run and bring it to, you know, so this is how the relay race works, right? And then whoever reaches the last, whoever manages to transfer this to the last person first wins. So this is the idea of entanglement swapping. So we want to do that same thing using entanglement. Instead of a baton, we want to swap entanglement. So what does that mean? So here I have an entangled photon source 1, here I have an entangled photon source 2. And so this source is creating a pair of entangled photons 1 and 2, let's say, for lack of imagination. And then the second source is creating another pair, let's call it 3 and 4. So now 1 and 2 are of course entangled, let's say in one location. 3 and 4 are also entangled. By the way, can you see me? Moses?
Yeah.
You can, right?
Yeah,
Because of course I'm actually explaining certain things in the air, looks like. So,
No, we are seeing.
okay, great. Yeah. So then you have the photon source here, and you have it here. And so 1 and 2 are entangled, 3 and 4 are entangled. But suppose these are at certain distance apart. Now what we do is we make 2 and 3 meet and do something called Bell state measurement, which I will skip. That is of course technical detail. So once you do this Bell state measurement, then 1 and 4 become entangled. Okay, so 1 and 4 were not entangled originally. 1 and 2 were entangled, and 3 and 4 were respectively entangled. But now by doing this Bell state measurement, you've made 1 and 4 entangled, which means you have actually increased the distance. So instead of just 1, 2, and 3 and 4, 1 and 4, which were obviously further from each other, have been entangled. So this is what is called a quantum relay. And now beyond a point, you can't take this quantum relay. So you actually need to put in some concept of a memory in between as well. So that you know, there is you can use it at will, so to speak, and that is the idea of a quantum repeater. So you have a relay plus a memory that will give you the repeater. Okay, and so this is the approach that we are also working on. So this is the relay with quantum memory also thrown in, and so these are various applications which one can do. And this is the project we are working on under this DST Quantum Enabled Science and Technology program. And so we are establishing quantum relays and in the lab, and then we are going to go on to swapping. And then finally, we are also going to show quantum teleportation, which is another way of quantum communication. So now this is a slide which I have from my friend here in Ottawa. So this tells you about, how much distance you can kind of go using these various things which we have been talking about. So direct ground-based links is moderate, right? So maybe up to 500, but I think realistically more like 3. And then low Earth orbits, satellites you can use for long distances, so 1,000 to 5,000. If you go higher, like a GEO or a MEO, then you go even longer distance. And then you can have quantum repeaters, again, intermediate distance. So the idea would be to combine repeaters and satellites together and form what we would call the global quantum network, or the global quantum internet. And that is what we want to move towards as a community, right? And so satellite as a trusted node, how does that work? So this is the general idea, as I was showing once earlier. So here you have a satellite. It has, so, essentially it exchanges a key with one ground station, and then it kind of moves to a different one, exchanges a key there. And then by performing certain operations on the key, you can actually have the ground station A and B linked with a quantum key. So you can actually form a quantum key distribution between 2 points which are much further separated than what you would get without using the satellite. So we're using the satellite as a trusted node. And that is much more trusted because it's, of course, much more beyond our control once it's up there, as opposed to having trusted nodes on the ground, which is this Beijing-Shanghai link. Okay, and so this is the idea of the intercontinental quantum secured network. So you can either have the source in the satellite and distribute the 2 photons between 2 receivers, or you can have the sources in the 2 transmitters, and then, one can go there. And then, so essentially either you have the source here or you have the source on the ground. And so these are called uplink and downlink and so on and so forth. And so this is the long-term vision. So this is, of course, what we are talking about here. But ultimately, we would like to see that, these are all exchanged from service providers to various services. And so essentially, you can see a diverse range that we have in mind, where people would use keys which are distributed using quantum key distribution. And so we can have one satellite, then a fiber network, and then link all of it together. That is the general idea. It's called the global quantum internet, which is the long-term vision. And quantum communication in space is, of course, real. It's not science fiction. And so, of course, the country which is leading in this is, of course, China. So they have already done many things towards quantum communication in space. So entanglement distribution over 1,200 kilometers, teleportation, QKD between Beijing and Graz. So they are the only country which actually has a quantum satellite out there, which is the Messiers quantum satellite. No other country has a quantum satellite yet. And then we have efforts from Japan, Singapore, Germany, Italy, Canada, and so on. So different types of demonstrations have happened from different countries, right? Okay, so what is the outlook of the Quest project, which is what we are working on? So this is the general idea. So you have, we want to do experimental implementation. So first we would do SPDC-based entangled photon source. We've already done that. Demonstrate in-lab entanglement-based QKD, we've done that. And then we've demonstrated a long distance free space entanglement-based QKD within our campus, which we are currently doing. And when you are allowed to visit, and when I'm allowed to allow you to visit, then you will see these portable ground stations on RI campus. And this will be the first step towards achieving satellite-based QKD and lays down the vision for the global quantum internet. And so this is the idea. It will come here, and then it will go somewhere else. And that somewhere else is actually, and so also the place we are also going to have this happen between India and Canada. And so one of the objectives of our project is also an international collaboration in which we will hope to establish a quantum link between India and Canada, which will be some 13,000 kilometers or so, which would hopefully we're able to do it. And then it would be a record in terms of the distance. So in this domain, one of the very interesting things, sorry about the in-press, it actually has now been published. So we'll see the publication reference in the next slide. I really should look at each slide before giving each talk, because this is now outdated. So I'll show you in the next slide if you wanted to have a look, because it's now online. And so this is a development which has happened very recently, not very recently, last year from our lab, which has now been published, which is called QKD Sim. Which is essentially a simulation toolkit for QKD with imperfections and its performance analysis with our own experiment on the B92, and how it matches with experiment is something we have also discussed. And so this is your Alice and Bob, and this is my student again coming up with a cartoon of, what is the most cost-effective way of implementing a QKD protocol, and that is something you can actually figure out using our QKD SIM. And so, and in fact, this made it to Times of India as well as a development. And so this is the publication reference, so please have a look if you're interested. And so then essentially, I'll tell you more about what that is. So now, simulation toolkit for QKD, there are some which exist in literature. So we have done a thorough search, and so these are all the ones which we have found, and I think it's pretty thorough in terms of the various ones. But then the point is, we have a certain number of requirements. So first of all, we want quick and precise simulation of physical processes, considering realistic experimental imperfection. Okay, simulation of the source, the detector module, and the background noise in more details, as well as the generalization and applicability to all existing protocols. And so there is no existing toolkit before this which actually satisfies all these requirements at the same time. And so why is this important or necessary? It is because, so now you think about it. So now that we have discussed quite a bit about QKD, and also there is a lot of discussion going on in different fora, I'm sure you're convinced that this is something which we should be doing. Not just we, but as a country, we should be working on it. And so if we want to do that, the first thing we want to figure out is, what should we be doing? I mean, it is fine to say that we should be doing QKD, but exactly what should we be doing? What is the protocol maybe we want to establish? How do we want to go about it? What are the components we want to put in there? And so in order to do that, of course, you can figure out, let's say you want to do some protocol, but then what are the components which you will put in there in order to establish something which really has a very good key rate and a low Q bar? And in order to do that, you would try and what would you do first before you buy components, which is expensive, right? You don't want to necessarily just buy and then realize that, oh, maybe I didn't want to buy this. It's not, it's much more expensive than that. So what you want to do is you want to do a simulation first to figure out what is it that I might end up getting as the answer to my key rate as well as the Q bar. And so if you want to do a simulation, then you will look for a simulation toolkit and you will find quite a few. But none of them actually bothers about the fact that experiments are not ideal. So if I use a beam splitter in my experiment, this beam splitter is assumed to be a 50-50 beam splitter in a normal simulation toolkit. But then I'm saying that no, my beam splitter is actually 48-52, which I know from, which is actually also true for some of our beam splitters. They can even be 46-54. So then what will happen to my key rate and Q bar? So each component that you use in QKD will come with its own imperfections. Similarly, the processes that you are using, whether it is development of a source or detecting a photon, it's easier said than done. There are lots of involved things happening in all these things. A detector is not going to detect everything you throw at it. It will not be 100% efficient. So these are the kind of things which you need to go into the simulation also. And that is something you cannot just do using something which is existing currently. And that is what we realized, in fact, the other way around when we started, 3 years ago when we were starting some of these activities in the communication domain, we were thinking, and then we realized that we just can't simulate and do this because it's not available. So we went and actually developed it ourselves. And so that is what QKD SIM does. It fills a gap, which is very important for a person who really wants to do this experiment or develop this technology. And then if I tell you that my key rate is 126 kilobits per second, QKD SIM is going to predict it in that order. But then a normal simulator, which does not take into account these imperfections, will perhaps tell you 300 kilobits. And then you will be sorely disappointed. And then if you want to use it for something, then of course your expectations won't match reality. So the expectations have to match reality. And for that, you need a simulation which is actually going to match reality. And that is what we fulfill here through QKD SIM, through processes, detailed processes and imperfections. And so this is the general idea. With QKD becoming commercially viable, advanced engineering techniques are being proposed. Direct testing of these techniques in an optical setup is not very cost effective. And so QKD SIM helps in quick accommodation and testing of these techniques by enabling simulation of QKD protocols, considering physical process models, realistic imperfection, and experimental non-idealities. And so we've tested its prototype's performance with an in-lab implementation of the B92 protocol, which is a prepare and measure based protocol. And we actually find it very interesting because there is also hardly much available in literature about simulating it per se. BB84, there is some literature, but not with imperfections. But B92, even that is not there. So we took it up as a challenge to actually simulate it and also do the experiment, because that itself has its own novelty. And so this is essentially the idea. Any QKD protocol, you can break it up into different modules, which would be used to simulate. And so what we have followed is what we call the AGIFAL, not what is the AGIFAL software model. So you have the waterfall structure, where you of course go top down, and then you bring in some agility in some of these modules, so that with new imperfections, you can just include that without having to change the whole simulation structure. So that is why we have the agile framework as well. So it's an AGIFAL model of software development. And so this, I mean, a little bit of a detail. So essentially the various things which come into different modules and so on. And this is the B92, which we just saw actually. So I'll skip that. This is a schematic. But having said that, this is what you will find, an example of rates that we have found around 50 kilobits per second, and a QBA, which is 4.79. And this 4.79 is very important actually, because the information theoretic security bound for the B92 protocol is 4.8. And so we actually have developed very dedicated optimization algorithms to ensure that our QBA is restricted to being below that. And so that our key actually has some hope. Otherwise, you can just say, okay, I have a certain key and I have a certain QBA. But what is the meaning of that? It has to have some meaning for the security purpose. And so that we've spent a lot of time on these details. And to our knowledge till date, the best available B92 setup has reported a key rate of 31.6 kilohertz and a QBA of 10.5%. And of course, we have 50 kilohertz and a QBA of 4.79 for a 2-meter transmission. So we are definitely better than what we know so far. And so these are the comparative results. And this is of course very important. So you can see, that key rate from experiment is also around 50, and simulation is also in that range. Otherwise you would expect this to be like 300 or something if you didn't do all these imperfections into account. And there are more imperfections that we want to now. So in the second version that we are now working on, second iteration of QKD sim, we are including even more, so that it becomes even closer to reality than what the first iteration gives us. And so this is the general idea. Yeah, these are photographs of the setup and how things look in the lab and so on. And these are snapshots of various algorithms which we have developed for QKD sim. So this is just a little snapshot of the entangled photon source which we have built. As I said, I won't get into the details of this setup because it's still not in the public domain. And so this is the BBM92 demonstration. And here you can see that our entangled photon source has a concurrence of 0.99. Concurrence is the measure of entanglement. So if you say that, I want sugar, then you would say I want 1 kilogram of sugar. So then if you want to see how close you are to 1 kilogram, then 995 gram is pretty close, because 1000 grams is a kilogram. That is the idea. So 0.995 concurrence is as close as one would get to 1 kilo. I mean, in this case, concurrence of 1. And so we don't know of any other source which has anything better than this currently. So this is the entangled source. And yeah, I'll skip the details of fidelity construction. Right, and so in the area of quantum communications, of course, we have India's first project on satellite-based QKD. We also have a project on quantum communications using integrated photonics. So this is a different domain. Instead of the long distance, which of course is a thrust area, we also want to be useful, let's say, to us. I mean, long distance is fine, we will demonstrate it, that's okay. But then suppose I want to use QKD personally, then maybe I will be relying on something which is small and portable. And so that is the idea of chip-based QKD, which we are investigating with our Italian collaborators under this program. And we are also working on quantum teleportation under the Quantum Enabled Science and Technology program of the Department of Science and Technology. This is of course me, but the idea was not to show that. The idea was that, this is the ITUT actually, which is under the UN. They have a focus group for quantum information technology for networks. And I am an invited member of this focus group. And what we are working on is development of standards for QKD. So international standards for standardization of QKD. So, so that we know that if we claim something, whether that is actually meeting a certain global standard or not. And so that is the idea behind this focus group. And these are some slides from a meeting that I was at in China last year as a part of this. And so this is this Beijing Shanghai layer, Beijing Vienna, this satellite based demonstration that I talked about. And then Russia also has some good efforts in QKD. And and so this is the Russian roadmap for satellite based QKD. And this is this Beijing Shanghai link that I talked about. So Beijing and Hefei, and this is Shanghai. They have been linked together by this 2,000 kilometer backbone. And this is an important slide because this tells you what the markets for QKD systems, which was independently done by an organization which just did that. You can look up their website, insidequantumtechnology.com. And so here you will find how we see the market grow among various sectors. And so a close-up will tell you that you have the military, you have the government, and then of course you have the other users. So clearly there will be a lot of strategic usage, and that is what we foresee even down the line. All right, so with that, I would like to thank you for your attention and stop speaking for a few minutes. Yeah. So Moses.
All right. Thanks a lot. There are a few questions in the chat. Like, you want me to read it up, or you
Should
can...
I stop sharing the screen?
Yes, yeah, that'd be perfect.
Okay. Yeah. Okay. Now I can at least see your faces. Yes.
Okay. I mean, either we can start from the above, but
sure.
Because you started about QKD, key rate versus Q bar. Can you explain that a little bit more?
Yeah. So so of course the key rate is of course the number of key bits that you produce per unit time. So let's say per second. So we have kilobits per second. So I mean when you talk about classical communication, we are used to megabits per second at least, if not even giga, right? So QKD key rates are always going to be lower than that for now, because the point is that what QKD gives us is not an advantage in transferring a lot of data very quickly, but it is about transferring data securely. So then you will not have at least for now, of course that is one of the open problems which others including us are working on, which is to try and get the brightness of these sources to go up. Because of course, at the moment we are restricted to how bright our photon source is. And so if that is in megabits per second, usually, then of course, boiling it down to, various things that will happen after that, the hundreds of kilobits is what we would have in the, in QKD. But then, so that is the kilobits per second. So that is very similar to the concept of, any key rate.
Right.
But then the Q bar is what is called the quantum bit error rate. So, a Q bar of 4% means that, there are 4 in 100, which are not quite what they should be. You understand? Like, so, I'm saying that, suppose you and I are exchanging a key. And so I have the key, let's stick to 10 because you can't just rattle off numbers like that. So let's say I have a key, which is 00011110100, just like that. And so you also have a certain key, and we feel that we have established this key between us. But then now if I have but then this may not be 100% so. So there will be a small error always in key distribution. And that is what that will happen due to various reasons. It need not be only because of eavesdropping. It can be simply, as I was saying, that is why this prediction is important as to how much I'm expecting with these devices. What I was saying towards the end about QKD SIM. So then these will bring in imperfections, and so something might flip. So maybe I have the 0, but there is a bit flip and you get a 1 instead. And it is not because an eavesdropper did it. It is also possible simply because of the fact that this is an actual experiment, an actual devices. It's not on pen and paper. And so that is the Q bar. And so up to a certain point, so there are security thresholds associated with different protocols. So for the BB84 protocol, for instance, there is an 11% conservative number. There you can also have a number of 25, you also have a number of 15. But then if you really want to be very, very sure that, you have something worth investigating, then you want to be below 11%.
Okay.
Because that is within the information theoretic bound.
Okay.
which we allow.
Mm.
Even if that is there, we could be okay, because then you can actually subtract off the cuber and you can get a cuber free key kind of, you know. But then beyond that, we cannot allow, because that proves that definitely there is more to it than just errors creeping in any experiment, because nothing is perfect. So that is the quantum bit error rate.
Okay.
Yeah.
Ma'am, you also talked about this high order quantum computing, where you know the quantum supremacy 2 to the power of 50. So either you can increase, like reach 50 faster, the qubits, or you can increase 2 to 3 and 3 to 4. So what's the higher order that we have reached at RRI? It's 3.
Well, at the moment we have a base 3 with an exponent of 2. So we have a bipartite qubit system. So we have 2 qubits which are highly entangled with each other.
Okay.
But then, of course, with our technology, we can easily reach up to 10. And in fact, this paper that I showed you, which got accepted 2 days back, that actually also has some details on that, how you can use such techniques towards increasing the number. So, I mean, you can see that, you know, a number 10 is already quite competitive. If you think about the fact that the bottom, that the number in the base is 2, is 3. And if I can make the number in the base 4, then I become even more competitive. So that is the general idea. And of course, before, you know, just on this same point, you have to appreciate that, you know, there is a lot of open things to do there. I mean, you know, in terms of the qubits, we already know what the gates are. We already know what is the universal set of gates. Many things are already known because we've been doing this for the last 30 odd years. But then the higher dimension is much more recent. And so then lots of open problems, you know, what would be the universal set and how would we do this? So that is actually very interesting from a researcher perspective.
Right. Okay, great. So that was the next question. So from a bunch of enthusiasts who already has like a background in computer science and technology mostly. So as a team, if you have to take like one problem and solve it, is there anything in the QKD domain? Because the last slide that you showed also, you know, like QKD is one area that the adoption has been growing, at least at the industry level. So what would you suggest, ma'am? So on research side, higher order computing, you know, those things.
Sure.
On let's say someone is thinking about a startup in this domain, quantum cryptography, then what would be a good area to explore or a use case to explore?
Yeah, this is something I would need to think a little bit more before I can give a well thought out answer, because you know, it could change. But then, of course, as I just said, that, you know, I think one of the things which so one of the problems with some of the startups which exist is that they are focusing on certain protocols which beyond a point do not have the right security analysis. Like, for instance, you will hear about something called differential phase shift based QKD, PSQKD, which is actually using it's a fiber-based system, but it is actually using a weak coherent pulse. And I actually said during the talk that if you want, we can discuss it a little bit more. So then the idea is that you have a laser, and then what you're doing is you're through some means you're attenuating it down so that you reach a domain where you have less than 0.1 photons per unit. So in some sense, the essential idea is that you are reaching a domain where you can say that, okay, maybe in this pulse, I actually do have a single photon. But the problem is that, you know, this is an average. So then there are going to be pulses in which you have multi-photons. And there are going to be pulses in which you have no photon. That is the one which will make this number go down to this 0.1. So this weak coherent pulse-based source has this inherent issue that it is statistically not a single photon source. So if you actually try to do this anti-bunching experiment, which is what we do to get the single photon character, where, you know, you have these, it's called the Hanbury-Brown twist experiment. It's also using cosmology. So you have a single photon incident on a beam splitter. It'll either go forward or it'll be reflected. It can't go both because it's one entity. So if you try to do a correlation measurement between these two, you will not get anything because it's gone this way, but here it is 0. So 1 times 0 is 0. And so that is the basis for Hanbury-Brown. So this is where, you know, you get a dip in this exercise, which you won't get using these other types of sources. So then if you use a WCP, that doesn't mean that you can't, you can use it. But then the problem is with this GPS type systems, they have a security analysis issue. So it would be nice if people actually concentrated on more established protocols, because there the security proof is very well known. But in order to do that, you need to do real photons, and that is perhaps why people don't do it in the first instance.
Okay. Yeah. All right, Deepthi, you want to ask your questions or you want me to read it?
Yeah, sure. Hi, ma'am. First of all, really nice talk.
Thanks.
Over here, like, I'm trying to work with tracking of orbital debris. And for that, I have proposed like a heat mapping, and where I have a constellation of satellites around the world, and they kind of form a network within themselves, and you track a piece of debris and identify it as it goes around using photometric methods. Now for this, I will also have to map the time lag between each of those communications. Suppose I want to implement a particular protocol of quantum encryption so that it's not snooped on or modified or tampered with in any manner. First off, how would I be able to do that? Would I need a quantum computer on board each of the satellites? Second thing,
but before you go to the second one, let me just understand the first one. So you have a constellation of satellites, and each the debris is something which is local, or I mean, so the satellites, each of them, they are orbiting and they are encountering this debris. Is that right? How is this working?
Yeah, so they are orbiting a geosynchronous orbit, and the debris is going in the low Earth orbit. So they're just monitoring the debris.
So all of them are monitoring the debris, and you want to figure out whether the satellite one, whatever it communicated to you, whether how it is related in time stamping with satellite 14.
Yeah. So it's basically like I want to find out that I identified the properties of this object over here to be this.
Right.
Now I need to know at least at one more or two more positions that this same object. So first I need to identify that it's that object. Second thing, I need to be able to compute the time lapse which happened so that I can get its velocity and hence the two-line element set. Once I have that, I can say that this object of this characteristics having identity this orbits in this kind of motion. So for that, I need to know the time lag. So first,
is how does quantum cryptography come in here? This is what you are talking about is actually very precise timing, where of course we can have atomic clocks, and that is of course an active area where you can actually use cold atoms to make atomic clocks, and ISRO is working on that as well. And so then this atomic clock based systems, and of course at some point, I mean, now they are here, but then ultimately when they get really commercial, then they can also fly, and then you will have this precision which is much more than what is currently available, where we are at a certain domain. So that is there is no encryption involved in this process. Or do you want to include it somehow? I didn't
get
that.
The thing is, like, if a particular agency like ISRO wants to monitor it, there are a lot of vested interests in trying to say that, especially when space policy gets implemented, when you're trying to penalize somebody for creating so much debris, there's definitely this thing, like if SpaceX has made something, they'd not want that debris to be identified. They try to tamper with the data. It's a possibility, hypothetically. So when you have that, you want to make sure that the data is safe, that whatever you're getting back there it's not been tampered with or it's not been intercepted.
But then in order to do that, you have to establish a key with the debris, right?
I'd have to
have, so let's say for argument's sake, suppose you have a key established between a satellite and the debris. Let's say, which of course you don't want to do, but I'm saying suppose you do that, then of course, if you're now encrypting the information that you're getting from your debris with this key, then there is a way in which we can figure out whether it is the correct one or whether there is some tampering. There your thing will kick in, all these principles that we were talking about and so on. But then how, I have to think about this more, because this is not a usual problem that I think about space debris. But then having said that, I'm thinking how you would ensure that what information you're getting is the correct one without having any initial communication with the debris is something.
Correct, exactly. So it's like I have this particular thing. I predict that for the next satellite in its purview, it will come at this particular time to this particular time, that transit will be there. So in that particular time, if the other satellite also says, yeah, fine, it's been there. So at that point of time, I can say, cool, my data is valid. If not, my data is not valid. So that is the basic thing of tracking.
Okay.
Now the thing is, I do not want some sort of tampering to happen with this entire network that's going on there. Because if some tampering happens, then all the data is compromised.
Maybe if some tampering happens, then what will happen is that you won't get this information at the time that you think you will get the information.
Yes.
And
so
then
I will miss that piece of debris and I'll not be able to find out that it's actually there.
Yeah, so that's what I'm saying. So then if this tampering happens, then it will basically also tamper with your timestamp.
Yes, exactly.
And if it tampers with timestamp, then we find out. But then we can find out if we can actually make this much more sophisticated in terms of not using the usual clock, but something which is 10 to the minus much better than whatever it is right now, which is perhaps 10 to the minus 9 now. I don't know what is the best that you have.
So what are the requirements? Like on the satellite, what are the requirements I'd have? And how do I vary this from a classical thing of satellites orbiting and this sending data to the ground station, we're processing it, done. So how will it change if I'm implementing QKD in this?
So now, if we actually get this constellation of satellites to be linked to each other through a quantum network, which of course has not happened. Yeah, but suppose we get that to happen, then of course these satellites share a certain link which no other party knows.
Yes,
so then
that is the idea.
Then they will be able to use this information to figure out whether what they received is coming from the right source or not.
Correct, yes.
But that is a little futuristic right now, but that is of course the idea of the global quantum internet. That we have a constellation of satellites. We are talking about one satellite for now, but then we will of course hope that this is so then, you know, Deepti, this is an interesting thing, because we would then hope that there is cooperation between countries to have this constellation. Or you can have a constellation.
Just one person. Yeah. It's just one. ISRO is having 3 satellites or something.
Then it's okay. Then it'll actually work. Because if you now want cooperation between different countries, then of course you don't know who is going to do the tampering.
Yeah, it's a big headache. You can't trust it.
Yeah, that is something which is the whole point of, you know, showing this in one go, with one satellite to begin with, and then having inter-satellite quantum network.
Also, like, will I have to factor in the time lag into the physics of tracking the debris? Like the time difference between this satellite to this satellite and this radius of the orbit corresponds to this velocity of the debris. Now, will implementing the QKD have additional time lag because of the processing that is happening?
No. Because see, the QKD is something which you would have established anyway, and then you already have the keys. So then we would assume that these guys are connected with a quantum network, and then they are doing the process that you want them to do, which is the tracking of the debris for the current discussion. But then it is not like you are going to
I think your internet is.
Yeah, just.
You still hear me? Can you hear me?
Yeah.
Yes, now I can hear you.
Yeah. Sorry, yeah. I think there was a bit of a connection issue. So what I'm saying is that, you know, that is where this concept of memory comes in. So we would establish these keys and then store them. Right. And so, of course, it's not yet happened. I mean, just to make it clear that, you know, these are all things which we're working on. So then, then we use it when we need it. And so when you are doing the tracking, then you use the key. I can share a slide with you. I mean, not here, but then separately, which tells you about the various stacks that happen in such a network. And so we are only talking about the key management layer right now. But there are other, there is this user user layer, and then there is the key manufacturer layer. So there are 5 layers, 6 layers in a simplified quantum network. And we only are talking about
each of those errors have to be taken into consideration then.
Yeah, and then hopefully those errors are not going to be very high, because, you know, if we also bring in an atomic clock, this is again a development which people are working on. Then of course the timestamp goes up by orders of magnitude. And so
that is one thing. Another thing is, is that required? If somebody has a quantum computer and they're able to intercept signals between these satellites, can they find out what I'm tracking, or can they find out the information and everything?
See, a quantum computer is, of course, not going to jeopardize quantum key distribution, right? I mean, the whole idea of quantum key distribution is to ensure that a quantum computer cannot run an algorithm from the known ones currently.
Exactly.
Can change. I mean, maybe there is some other algorithm, but at the moment we are talking about the Shor algorithm, which will run on quantum computer, which will not be able to break QKD, right?
Yeah. So the thing is
a threat for us here.
So the thing is, QKD is necessary, right? Like
I would
need
definitely
to
say so. Otherwise, I'm out of a job. But then, on a more serious note, you see, that is the point. So if we follow the track, then quantum computing is also necessary. So quantum computing is necessary to do the things I want it to do, but then it is also going to do a few things which I don't. And that is why QKD is necessary, to counter that aspect of the quantum computer, which it will inadvertently also possess. But then, having said that, you know, there are other means by which people are trying to make even better classical algorithms, which is also going to be quantum computer resistant. It's called post-quantum crypto. Okay, and that is another area which is also very interesting, but then it's not as developed as QKD.
Right.
QKD has lots of users and use cases around the planet, but then here it's not quite there yet.
Could I send across my mail ID on this chat, and could you share those slides and this PPT as well with me?
I think I'm stuck. Deepti, you can ping me. Yeah.
Can you still see or hear me? Or
yes. Now
okay.
it is.
Yes.
I don't know what.
So I was just asking if I could just send my mail ID on this chat, and you can send me that stuff, you know.
Yeah, I can send you. I mean, it's just one slide I prepared for. Or what I can do, Deepti, there is a. As I was telling you, I'm a member of this focus group for standardization, and so I gave a talk last week in this UN discussion panel. So that actually has this. So this is a it's essentially an open for everyone. So you can hear the whole talk, and you'll get a lot of information about this and other aspects of QKD and networks and all. So I can send that link to. You are the one, Moses, who is quantum computing in India?
Yeah, I'm mailing.
Okay, because it comes from this nameless thing, right? So then I will send it to that ID, and you can share with Deepti.
Sure. Yeah.
Because it's free. I mean, I guess you need to give your user ID and email ID, and not user ID. You have to give your name and email ID, and then they'll allow you to see it, which is fine.
Sure.
Yeah.
Sure.
Okay. Yeah, great.
Yes, ma'am.
This is another interesting question. Can quantum key distribution phenomena be used for quantum random number generation application, say for QR codes?
It's the other way around.
Oh, it's the other way around. As non-cloning theorem is valid for QKD.
No, cloning theorem is valid for QKD. Of course, it's valid for QKD. It's not valid. It's essential.
Right.
For certain aspects of QKD. So quantum random number generator. So, I mean, I think even when I was showing you the animation, you must have realized that I was saying that Alice randomly selects a basis and Bob randomly selects a basis. These are words I was using. So she selects randomly a basis out of 4 to encode, and then Bob also does that. So this randomness is very important. And so how do you get this randomness? So in fact, in the paper, in this PhysRev applied one, we have actually used quantum random number generator to generate this randomness. What is more usual is to use the algorithmic ones, like which we call pseudo-random.
Right.
So you can just write a code, right, on MATLAB or something, and you can generate random numbers. So that is something you can use, but then it's okay. But if you want to do it better, because those are also not really, they won't pass all the randomness tests.
Correct.
So if you want to do something better, so then you use a quantum random number generator. And so that is what we have used. We have used that, we have made that, and we use that in that protocol. So quantum random number generator will be very useful to increase the security of QKD. Because beyond a point, if the randomness itself has a question about it, then of course the whole thing has a certain error associated with it. So that is, it's the other way around.
Right.
Yeah.
Okay. All right. Mahima, you wanna ask the question?
I can ask.
Yeah.
Hi, good evening, ma'am. It's so exciting to have a talk with you over here. So my question is actually, whenever I have been reading about BB84 and QKD protocols, the doubt I had is like we are depending on an authentication channel always, and if somebody, a attacker who is capable of doing everything on a authenticated channel exists, aren't we actually making the security of QKD equal to that securing that authentication channel?
Yeah, that's a very good question, Mahima, right?
Yeah, ma'am.
Yes, that's a very good question. And in fact, this is the same thing I was saying, that there is always a seed key that is required. And that is where this authentication comes in, right? That is the seed. And so this is something which we say, which we already somehow magically possess in the beginning. That is how we go about talking about this, right? But having said that, suppose there is an attacker who is doing this, the worst he can do is perhaps succeed. But then what we can do is not take that key.
Okay.
So that is what we do, in fact, so whether we are attacking the actual the key distribution part or the initial key part, which is what you are talking about, that is the initial authentication that you need to do. And so either way, there are ways in which we will of course know. And so then the worst that can happen is that we have lost some time, because we decide that no, this is a key which we won't use. And so we will not call a quantum key distribution successful unless the quantum key is established. So we never say it is transferred, we say it's established between Alice and Bob, because that's what we do, right? Like, so both of them end up having the same key. You get that. And so then the idea is that if this is happening, and then we will know from the error analysis, then we will just avoid it. That is the idea.
Okay.
Because we do need that. You're right.
Yeah. That was always like we try doing
it's a chicken and egg thing.
Yeah,
it's always a problem, because in the beginning you always need the seed when you study, and then the seed is something which you have to live with. And if somehow that seed mathematically establish that these things have happened, but then the only problem is then you have to ignore that key that key establishment. So that is the advantage we have in QKD, that we are not forced to accept a key unless we feel that it is satisfying the error threshold.
But again, the question I have there is, we can actually detect the presence in a quantum channel, but in the classical channel we cannot.
But that's the point, you see. So if there is something in the classical channel, then that is of course feeding it. Ultimately, the quantum channel is the one which establishes the key. The classical channel is necessary for certain aspects, right? And so then it will actually show up in the ultimate protocol.
Okay.
And then we are able to discard it if we. That is the point. So then this power that we have to discard, we don't really have it otherwise, because here we can do it before we use it for some sensitive communication. And otherwise, in non-quantum thing, you won't know that, right? So that is the general idea.
Next question is from Aniruddha. He has a physics background, and his question is, for two-dimensional Hilbert space, we use polarization states, the horizontal and the vertical. Talk about qubits. What are the physical properties of the photons used to prepare higher dimensional Hilbert spaces?
So the physical property that we would use is a spatial degree of freedom, for instance, or you can use orbital angular momentum. So photon has something called orbital angular momentum that in principle has an infinite dimension. So you can truncate it down to lower, and that has its own problems, but that is one way. Or you can go bottom up like we are doing with spatial dimension. There you can, when you have 3, you have 3, and if you have 4, you have 4. For orbital angular momentum, if you bring it down to 3, there's a little bit of the rest of the dimensions lingering there, which causes a leakage problem. But anyway, we won't, so that is the answer.
Okay. Nilay, Abir, Nilay?
Yes, hello ma'am. You had a great talk. So I had just one question, like it's better, like there are many multi-qubit systems, like we talk about qubits, qudits, and qtrits.
Yeah.
Qubits has two, qudits have like the deep possibilities, like it goes on varies. So should we design a system which has more possibilities, or should we design a system like where we have more number of qubits, like have a system like for qubits has two, and there's something which has 10, like it can be in 10 different states.
Hmm.
Have that one like in the system, or design a system where you have like hundreds of qubits, so you get that equal, like you have the maximum possibilities in the state. So
Depends on what is your purpose and who's funding you.
all
I mean, this question is not complete, is it? Yeah. So the point is that, if you are interested in just saying that, okay, now, that is, I mean, I'm in this draft committee, right, for the national mission. So I won't divulge details, but then having said that, there is this thing that, oh, India needs an X qubit quantum computer in Y number of years because Z country has done it. If that is where you come from, then build the qubit based one with more number of systems. But of course, if India needs to do something which others have not already done, then I would spend some time in the alternative approach, because it's not guaranteed success, you see. So if you want to satisfy that, well, we need to do both, in fact, under the mission, so that we satisfy that group of people who want those numbers to declare them in the 15th August speech. Or on the other hand, we also need to have these, niche things happening so that other countries can declare them in their speeches, right? So then I would say, please go for both, depending on the answer to my question as to where you are coming from. Right?
thank you, ma'am.
You're welcome.
All right, Abir.
Hello, ma'am. Great talk.
Hi.
It was really great talking to you. And
No, you haven't yet talked to me, but then I'm glad that you liked what I said to you. Yeah, thanks.
listening your talk.
Yeah.
So I actually had a question on quantum memories. So you mentioned that quantum relays use these quantum memories. So I mean, seeing the quantum nature of particles, the decoherence time is something which is very small. So like the coherence actually stays for very less time in any quantum system.
The coherence time is
So the coherence time is small. So how do we actually make these quantum memories? Because memories needs to store some data for a longer duration of time. So,
that's a very good question. So I mean, how do we make this quantum? There are lots of different physical systems that different people are exploring, and so there are some which are based on certain molecules which seem to have a higher lifetime. And then there is this atomic memories where, you take an atom which kind of stores something. So these are all, so the exact problem that you have highlighted is the problem right now, that we really don't have memories which are lasting. So when now suddenly somebody says that we have a memory which is lasting seconds, that is great, because we are still mostly in the microsecond domain. And so this is so then, the quantum memory research is very interesting, because on the one hand, there are some known systems which, I mean, if you just Google, you will find some common ones. But having said that, all of them or most of them are really very short-lived. So you can't, it's a very short-lived memory, and the memory which is short-lived is not good even in quantum. So then one of the open areas is to find new possibilities for memory. One of them is EIT. That is also another electromagnetically induced transparency, it's called. So that is another way in which you can make a quantum memory. So these are, what we are doing as a community is we are coming up with systems where we show that, yes, okay, this has been achieved, that, okay, this has been stored and now I can retrieve it. But then the time is really very short. So indeed, it's an open problem as to whether we will really have something which stays for long enough. Otherwise, of course, that is why I said, the quantum repeater and memory research is more at a research domain. Whereas, of course, satellite QKD is also very much at a research domain for most people, except that we have a successful demonstration from China.
Another thing related to this, so we know that in quantum world, there is no cloning theorem. So how do these memories work exactly? Because if we can't clone the state, then how can we?
No, you actually store the information, but then you don't really try to copy it after storing.
Okay. So
and also Nilay, yes. Now I don't know who I'm talking to. What is it? Abir, yes, because your name is not coming. Yeah. Okay. So then one thing you have to understand is that no cloning theorem is for a certain class of states. So you can't clone certain states. But then, of course, if you can relax that condition a little, some things can be cloned. So only certain unknown quantum states cannot be cloned.
Okay.
Okay, so that is the idea of the no clone. And because Eve doesn't know, that is why she can't clone. But if it's a certain known state, then the no cloning theorem is not quite applicable. So that is where you can find your answer.
Okay. Thank you.
Archit, do you want to ask that?
Yes. So, good evening, ma'am. A really nice talk.
Thanks.
So, I'm totally new towards quantum cryptography and everything. So, just a curious question, because we are talking about satellite level communication, and because of the distances coming into picture. So, while these algorithms like QKD and other algorithms being experimented, so are there any relativistic effects happening, which should be taken into considerations?
Yeah, that's of course also a very, very good question. So then, that is one of the things. So this entanglement, that is actually a problem which remained an open problem for a long time. And recently, Singapore has sent up a satellite called Spooky, with Q, not K. So Spooky, where they have actually shown how entanglement is behaving in space and all. So essentially, it is related to your point that, these quantum effects, which we are kind of relying on, how does gravity affect them or lack of it? So then this is the kind of thing. So there's a lot of, in fact, this is one of the things in which people like us are very interested to come up with new ideas, which perhaps could be explored with such, with the scope that we have, with the projects that we already have. And of course we will do key distribution, but then, how much, how precisely, relates to what I said also, that, how precisely these various laws actually hold is something that is of deep interest to us. But we are only able to test them where we are currently. But then one of the things we would like to do, and of course there is a lot of discussion on that as well, is to come up with interesting tests of that in the satellite. Because that is where we don't know. There is no a priori reason for things to change. But then again, nobody has had the opportunity of trying it either. It's not easy to just try something on a satellite. It requires a lot of funding as well as impetus. So then, in some sense, this is a very good question. You should think more, and if you have ideas, we should discuss. Because this is one of those things in which we really, of course, that Spooky thing, they have proven that yes, it is kind of maintaining a certain fidelity that we expect. So maybe nothing new is happening for now. But then again, if you increase the precision level of those tests, then maybe something creeps up at the fourth order, and that itself is fantastic. This LIGO, one of the things that we have in mind is to have LIGO in space. So essentially, these are all related to that, but at some point much more difficult to actually test out. So we need to flesh out these ideas with a lot of math and a lot of feasibility, first of all, where we are, because there we have much better access. And then, something will become a candidate for testing it there. Because you rightly say that, how do we know that something doesn't change really? And then, of course, it will have an effect on QKD, for instance.
Yeah.
But for now, the problems that we are working on, or what not just we, anyone is working on, is more about establishing that these things actually are working. Because the fact that we can have QKD between two ground stations is itself very new. So then, and before all this happened, in fact, someone like me, I have been trying to pursue or persuade people to fund a project like this here from 2013. And so then I was told, एक photon जाएगा, फिर कैसे वापस आएगा? आप कैसे क्या बोल रहे हैं? So that is the thing. So then, I think your questions are great, and it is directly proportional to the fact that you are very young. And of course, when you grow slightly older, then you realize people are actually worried about much more basic things. So first we have to satisfy those, then we'll get to these questions. But then having said that, these are the questions which are more interesting. So it's very nice that you're thinking about it.
That should be nurtured,
Yeah.
One last question.
Great. Okay. Bolo.
No, this is relevant to what's the route, or like, being able to work with you in the Quest project? What skills and knowledge one should have to get there?
The Quest project, of course, is a project which has a non-disclosure agreement. So I don't know. I mean, so if you want to work in the Quest project, then you better apply for one of the open positions and join the lab. That is one way of doing it. But having said that, it's not just about that project, right? So we, of course, are working on several areas of quantum communications, and they all feed into one another. This particular project is with space agency, so we have some requirements that we don't really, but then of course we are also pursuing things where we are, some aspects of it we are discussing and doing it with other people. So that is not a problem. So long as, there's this somewhere misplaced notion that, somebody will get to know and something will happen. But that is the whole point of quantum, right? That if we get to know, then nothing will happen because we won't let it happen. So then, but then of course this dichotomy exists. And so that is why we have certain, what should I say? Non-disclosure stuff going on because it's related to the security aspects, and people will use these results directly for security purposes, right? Various agencies and so on. But then having said that, we are doing many things towards it which are not really directly hampering this, and so it will be good to discuss possibilities. But I haven't thought out the answer
at
today.
the interface of this and space science that's something
But that
I'm
is the
really
project, right?
Like, what are the aspects that could be worked on? If you could just tell me, like, what are the skill sets that person requires? What do you look for?
See, the Quest project is a very interesting example of something in which we have an aggregation of different skill set people in the same project. So for instance, we have, our own PhD students who are naturally coming from a physics background. Then we have project engineers who are coming from electronics and communication engineering background. Somebody has done an MTech. Somebody comes from a computer science background for simulation. And then we also have people who are coming from math background. So we have different types of people who are working together towards this. So indeed, so long as you have some kind of unless you are a biologist, we don't see the need for it yet. But having said that, engineering, physics, mathematics, these are all coming together. And so in some sense, all these skills are very relevant. And of course, we have ISRO as our partners here. So they are filling in towards the satellite end. Because that is not what we do for a living, and neither do we kind of wish to, start making satellites. So then that is where they are playing a role. And so it's a synergy. And so indeed, this is beautiful because, in some sense, people, but then also very interesting if you have a group meeting, because sometimes people don't understand each other. But then having said that, different skill sets are finding a very important role here. We also have someone from IIA, for instance, who will come in, who has a different skill set, like telescopes, So you understand, so there's a lot of, so it's not like one thing. So for instance, if that were the case, then I wouldn't be the PI, because I don't build telescopes myself. So then that is the point, you see. So then in some sense, it requires different skill sets. And so that is why it is very nice and exciting for me, because I learn from so many people.
You talked about QKD SIM. Is that open source?
It will be in, so with this question being perhaps the 17th time I've answered this question in that many days, we are definitely working on that, and hopefully by the end of this month.
End of this month? Oh, lovely.
Yeah, because, because we have had these requests from very affable people like you, and also very people who are from agencies which won't name themselves, type.
Okay.
Yeah, and so then we are saying that, okay, fine, let's make this happen. And so we are actually accelerating that to a certain extent.
Ma'am, I had asked you this in May, but I just wanted to ask you again. I'm Dipti.
Yes, I know you're Dipti, but then the fact that you asked me a question in May is...
I wanted to ask, like, is there any opportunity to work on something with you, or be able to learn something from you, if you could just...
I don't know whether you learn something from me. That just means that I have to know a lot, so I can't just comment on that. That is for you to figure out. But then whether you can work, so so maybe you should remind, maybe that was in an email then, because if you asked me something in May, it couldn't have been.
Yes, it was
so
an email.
Maybe it is a good idea for you to connect that once more, because unfortunately for me, it's really bad, but then there is a lot of interest and lots of people do keep writing, and sometimes I just end up not being what I should be about it, which is, you know, very conscientious and reply to everything. It just doesn't happen. So maybe this just fell into one of them. And May is a bad month, right? Like we're all very sad people in May. Yeah, so then maybe that has something to do with, but then yeah, so sorry about that, Deepthi, but then I'm sure
No
I
issue. No.
saying sorry to so many people. So if you wanted to just put this in context of today's discussion and write to me, then we can see if where
Sure.
this will go, right? Yeah.
Definitely.
Yeah.
Ma'am,
Yes, Moses.
open for just one more question from Achit.
Just about the last question. Yes.
Just about the last.
Yes. Yes.
Because we don't get to do this often, so you know.
No, it's great. Yeah, it's very nice. Thank you. Yeah. Yes,
Ma'am, I'm sorry to take your time.
No problem.
But
yeah.
So, ma'am, recently, actually, I wrote an abstract, and the paper named as Quantum Computing and LIGO, and it got accepted to the International Astronautical Congress.
Okay.
So,
that's nice.
So, ma'am, the idea behind the paper was actually to integrate the methods and algorithms of quantum computing to actually analyze the data of the LIGO observatories. Like, specifically speaking, what I had in my mind was to optimize the data that we are getting for an effective classification of the gravitational wave data. Like, we classify the data into like binary black hole merger or a black hole neutron star merger.
Yeah.
So me and Abir, we both are working on that paper right now. And the major problem that we encountered while we started off with the paper was that there was no literature available on the internet related to that paper. And as of now, we are kind of struggling like how to even like start off with the paper, because we have an idea in the mind, and because we are kind of immature in our fields and we don't have proper experience. So I just want your view, like how can quantum computing be integrated in these kind of processes, like in LIGO?
Yeah, that is why I'm trying to figure out while you speak. So how exactly are you proposing to use a quantum computer for LIGO? What we have in mind is, of course, changing the state itself to, let's say, a squeeze state. So, you know, so LIGO, we are using laser-based interferometry. So if instead of that, you actually changed it to a true quantum state, then it might bring in some quantum enhanced sensitivity in LIGO. So that is the kind of, that is feasible. And of course, the Caltech group is also working on this. You know, they have an important role to play in LIGO, right? So that is what I'm saying. But then I'm trying to think as you speak, how quantum computer will help. So, you know, you have the data. Are you saying that you want to use the quantum computing in a data analysis platform, as a data analysis platform?
Can I pitch in here?
Yes, yes.
I'm Abir, so I'm working with Archit on this.
Yeah.
So actually, it was more like maybe whatever processing we do after measuring the data, if we can transform it into the quantum domain, we can do that processing maybe before that laser hits the photodiode for measurement purpose and before the wave collapse. So would that bring out new perspectives of, or maybe new way to see to the gravitational wave?
But then, Abir, if you wanted to do a measurement before the wave, before it hits the detector and so on, again, I don't understand the role of a quantum computer in this. It's a quantum process, but then are you interchangeably using a quantum process and a quantum computer?
Not exactly quantum computer per se, but
then
maybe
it is easy, better.
Yeah. So I mean, it's a quantum process. So let's say we measure the intensity of the light in LIGO, and then we perform your FFT, and then whitening of the data, and then inverse FFT. All
but that is what I was saying. That,
so all these processes, if we can transform to the quantum domain, that is before
but that is what I'm saying. So now before the laser hits, so the whole one of the things which one is toying with is the idea of changing the source from a laser to a quantum source. So that is the analysis that one needs to do. That, you know, and do look up any new, because this is not my direct area, of course. So I don't. I mean, of course, I can look up, but then you can also look up whether there is any paper which has come out from Rana Adhikari at Caltech. So he's the one who's been looking at this, and in fact, he visited us last year also. And so then the idea would be that instead of using a laser, if I change the source to a squeeze state, which is a pure quantum optics state, then I expect enhancement in the precision that I will end up getting in LIGO, because LIGO is all about precision interferometry.
Yes.
So this is also same in the same genre as what you're saying, that you want to change something before it hits the detector, not in the post-processing.
Yes.
And so what we are saying is that we can change the source itself, because ultimately it's a so somebody perhaps, Moses has found a link for you maybe. So so it is a Michelson interferometry, right?
Yes.
So then beyond the point you can't change much except you change the source. Because what else will you change? I mean, you know, you can't change the mirror to a quantum mirror. I mean, you know, it doesn't exist as of now.
Yes.
So then that is where, I mean, you know, that there's a lot of discussion on that, and in fact, it will be good for you to. I mean, you know, you guys are all doing projects, and also that is a very interesting thing to do, to have a state-of-the-art understanding on where the community is with this aspect of changing LIGO to a quantum version. But then from what I know, the quantumness will come in at the source level and not at a computing level. Because see, the quantum computer is not a computer which will make everything better for us. It is just a few dedicated algorithms which will work way faster. And that number is also not very high. So it is not right for us to say that, you know, once we have the quantum computer, our classical ones will not be necessary. It's not going to happen at all. So that is why I don't see the particular use of the quantum computer in this, but I have to think more to see if I'm missing something.
I mean, how I see it as is like when the light hits the detector, it's basically multiple photons hitting the detector, and it's sort of like a sampling thing. So if there are less number of photons, the brightness will be less. Thus, we get
no, it's not just that. It's not just
like,
that.
I mean,
so you have different limits of precision. So you have what is called the Heisenberg limit and so on. So do have a look at that.
Okay.
So there is a proportionality of 1 by n, and then there's a 1 by square root of n. And so in fact, if you go quantum, then you have more precision, and that is a known problem thing. So that is what people are trying to see if that can be used in a quantum. If you change the source, then of course you will have that regime where you will have 1 at a time, and so that is what you should be looking at. Okay. These limits, yeah.
And I'll have a look.
Great, yeah.
Thank you.
You're welcome.
Thank you, ma'am.
Thanks.
Thanks, guys. Ma'am, thanks a lot. So a couple of things I had to do. One, like put you and Deepti in touch about that May thing, and then Achit and Abir, if you guys can write like a abstract of your thoughts and then like send it to Urbasi ma'am, like it'll be easy for her to point in the right direction as well.
Sure.
Ma'am, and the main thing is the use case that we can work on. You said like you'll think about it.
Yeah, that is something I have to think about, because of course, yeah.
Yeah. So that, also I'll start one mail thread so that we can keep bouncing off ideas at least. By
sure.
Then if we can get like 1 or 2 use cases that the team can work on, that'd be great.
Sure. Yeah. So that I have to think a bit more than, impromptu. Yeah.
All right, man. Yeah. Thanks a lot. It was lovely.
Thanks a lot. Yeah. Thanks a lot, everyone, for coming in. Yeah. So
Thank
see
you.
you then. Yeah.
Yeah.
Thank you.
Thank you.
All right. Thanks,
Thanks, ma'am.